Okay, to start off with our bell work, we're going to go ahead and reduce these complex numbers. So this one is just a negative number under a square root symbol. So remember, we always take care of this negative sign first. So that's going to come out, because remember, by definition, square root of negative 1 is I, so that's going to be I square root of 96. And then we're going to break square root of 96 down. For those of you that are good with your multiplication facts, you might remember that 16 times 6 is 96. So that's going to turn out to be 4i square root of 6. If you didn't remember that, remember I usually try to look for 4s and 9s. So if I was like, oh, I don't know what factors of 96 I want to use, I probably would have done 96 divided by 4, and that's 24. So that would have been I, or 2i square root of 24, but then you would have had to have done that again and used 4 times 6, square root of 4 is 2, bring that out, and you get 4i square root of 6. So you could get the same answer using 16 times 6 or 24 times 4. Either way, just more steps if you don't pick the biggest perfect square factor. Okay, over here, the only thing wrong with our division problem is, remember, we're not allowed to have our complex number in the denominator. So we're going to multiply the top and the bottom by the conjugate of the denominator. That's going to eliminate our i's. So we're going to go ahead and remember, conjugate is just taking the opposite of the imaginary part. So I'm going to multiply out the bottom first. So 3 times 3 is 9, 3 times I is 3i. Then I'm going to move over here. A negative I times 3 is minus 3i. And a negative I times a positive I is a negative I squared. Keeping in mind that I squared is equal to negative 1. So that leaves me with 10 in the denominator. These two add to 0. 9 plus 1 is 10. So my denominator is 10. Okay, let's finish the numerator. 4 times 3 is 12. 4 times I is 4i. I times 3 is 3i, and I times I is I squared. Remember, I squared is negative 1. So 12 plus a negative 1 is 11. And 4i plus 3i is 7i. So there's our answer. Okay, what we're going to do today is we're going to graph these complex numbers in a plane. So just like we graph real numbers in a plane, we're going to graph the complex numbers in a plane. So when we're graphing a complex number, we change our axis names. So instead of calling this right here the x-axis, we are now going to call it the real axis. And going the other direction, instead of calling this the y-axis, we're now going to call that the imaginary axis. And then that's how we're going to graph our complex numbers. The real axis is the a part right here in our complex number. And then the imaginary is the b part, this part right here. That's our y value, okay, that we're used to, x and y's, but we're going to do a's and b's. So if we're going to graph negative 3 plus 2i, let me erase this stuff here. I'm going to go left 3 because this is the real part, remember? So this is the real and this is the imaginary. That corresponds with the old x and that corresponds with the old y. So I'm going to go left 3 and up 2. And that's my complex number right there. That's negative 3 plus 2i right there. Okay. If I'm going to graph 5, that's just the real part. So 1, 2, 3, 4, 5. There we go. Negative 6i is just the imaginary part. 1, 2, 3, 4, 5, 6. So it goes right here. And then 4 minus 2i, I would be going 4 in the real direction. 1, 2, 3, 4. And then down 2 in the imaginary direction, and that would put you right here. Okay, so it's just like graphing an ordered pair, basically. You just have to keep track of, are you moving in the real direction or the imaginary direction? Okay, notation when we're working with complex numbers and we're graphing them, a lot of times they will use the letter Z just to represent any complex number. And then Z with a line above it, that notation means conjugate. So we've studied conjugate, we know what that means. So for example, if I said Z equals 5 minus 6i, and then you saw this notation with a bar above it. That means tell me the conjugate of z. Well, the conjugate of z would be 5 plus 6i. So that's just notation that you have to know. That line above it means conjugate. All right, so over here it says identify the complex numbers represented by each point. So we've got 5 letters, so A, B, C, D, and E. Okay, so remember you're going to move in the real direction first. So to do A, you're going to go left 2 and up 3. So it's going to go negative 2 plus 3i. We went in the imaginary, so left 2 in the real, up 3 in the imaginary. Okay, so B is going to be positive 2. Oh, whoops, I just erased the E. I can put that back. Okay. Then I just erased those two. Not having much luck here. Let me put those back. We'll just leave those lines there. Okay, so B is over 2, up 3. So this is to the right 2, and then up 3, so 2 plus 3i. C is to the left 1, 2, 3, 4, so negative 4, and up 1, so that's I. And then D is to the left 4, and down 1, so that's subtract I, or minus I. And then E is 1 to the right, so it would just be 1, the number 1. Then here it says which 2 points on the complex plane are conjugates of each other. Well, if you were to look up here where we actually wrote them out, you can see that C and D, the imaginary parts, are opposite in sign. So C and D are the conjugates. But look what happens geometrically when you come over here and look at points C and D. They are reflections over the real axis, which makes sense, right? I mean, if a C value, if the imaginary value is positive, then its conjugate would be negative. So geometrically speaking, conjugates in the complex plane are a reflection over the real axis. Okay, so this says if Z is a complex number, compare the locations of Z and the opposite of Z in the complex plane. Okay, so let's just make up a Z and see what happens. We'll make up a couple of them. So let's say Z is negative 3 plus 2i. So then that would mean, now notice this notation here, this is the opposite of Z. So opposite of Z would be multiplying those both terms or both parts by a negative. So this would be a 3 minus 2i. Okay, let's do another one. I'll do a different color. Let's make Z 4 minus 7i. Okay, let's do the opposite of Z. Well, that's going to be minus 4 plus 7i. Okay, let's just graph those and compare what's happening. So negative 3, left 3, up 2 is right here. So this is Z. And then the opposite of Z is to the right 3 and down 2i right here. So that's the opposite of Z. So algebraically, opposite of Z means you just change both signs opposite of what they were. What's happening geometrically? Let's graph the other one and see if we can compare anything. So this is 4 minus 7i. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So here's Z. And then the opposite of Z would be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Right here. So geometrically, what's happening when you multiply by a negative? So if you take any complex number, so generically speaking, so let's say if Z is A plus B, then the opposite of Z is going to be minus A minus B, or negative A subtract B. We're going to take the opposite of both of those. What happens geometrically? Looks like it's a rotation of 180 degrees around the origin, right? Or you could say it reflects both in the X and the Y. So you could take this Z right here, reflect it in, I guess not X and Y, sorry, imaginary and real axis. So you could take this Z and reflect it over here to here, and then you could reflect it, oops, I'm in the wrong color. I was doing the green one. So it could reflect over here. to here, and then you would reflect again. So that would be reflecting over the imaginary axis. And then you reflect it again. So we reflect here to get to the third quadrant, and then we reflect here, get back up to the second quadrant. So two reflections. So you could say you're reflecting in the real and imaginary axis or rotating 180 degrees. And that's what happens when you have the opposite. Oops. Okay. All right, so here's just some algebraic manipulations of complex numbers. So notice we talked about z and the directions. They're giving you another complex number and they're calling it w. Same rules hold true if you change the letter. You can have the conjugate, you can have the opposite, all of that. The notation will still be the same. So first question up here on the left says take z and add it to w. So usually what I do is whatever the complex number is, I just put it in grouping symbols. So this is saying z plus w. So I'll go 3 plus 2i plus, and then I put grouping symbols for the other one. W is -1 minus 4i. That's going to help me keep everything in it grouped the correct way. It'll help my signs stay correct. So then from there, all I do is combine like terms. So 3 minus 2i is 2, and 2 plus a -4i is subtract 2i. So there we go. We got 2 minus 2i. That's z plus w. Okay, so same thing over here. I'm going to go z minus 3w. So z is 3 plus 2i. Subtract 3. Now notice, here's my grouping symbol around the W. I'm going to put subtract 1 minus 4i. As long as you put that in a grouping symbol, if you put your complex numbers in grouping symbols, then your operations, your signs are going to be correct. So now I'm just going to go ahead and do my algebraic operations. And we're going to go ahead and say, well, 3 plus 2i, I'm just going to leave that 3 plus 2i. I'm not doing anything with that. But this -3, I'm going to distribute that through, and I'm going to get plus 3 plus 12i. And now I'm going to combine my like terms. 3 plus 3 is 6. 2i plus 12i is 14i. Okay, down below, we're going to do the same thing. So on this particular one, can't see my numbers very well, but so this is saying not z, but the conjugate of z. So in grouping symbols, I'm going to put the conjugate of z. Well, 3 plus 2i is z, so the conjugate of z must be 3 minus 2i. So I'm going to do 3 minus 2i. Grouping symbol, and we'll put w, -1 minus 4i. And then let's just combine our like terms. So 3 minus 1 is 2. And then a -2i minus 4i, add those two together, and that's a -6i. So over here on the bottom, when I do this one over here on the bottom right, remember I'm going to put grouping symbols when I substitute in for those complex numbers. So I'm going to go 2 times z, which is 3 plus 2i, minus 3. Now I'm going to put a grouping symbol, and I'm going to put my w in there, so a -1. And oh, it's got to be the conjugate of w, so I'm going to do -1 plus 4i, not subtract 4i. Okay, let me raise that up. Now I'm just going to go ahead and do the distributive property, so 6 plus 4i plus 3 minus 12i. Combine my like terms, and I end up with 9 minus 8i. Okay, same setup again. This time we're doing the conjugate of z minus the conjugate of w. So conjugate of z is 3 minus 2i minus grouping symbols. Conjugate of w is a -1 plus 4i. Combining our like terms, so let's go ahead and do the distributive property first. So we're going to go 3 minus 2i plus 1 minus 4i. And then I combine like terms, and I'm going to end up with 4 minus 6i. Okay, over here, because this conjugate bar is over everything, what I'm going to do first is the z minus w, and then I'm going to take the answer of that one. So what I'm going to do is z, so z is 3 plus 2i minus w, which is a negative 1, subtract 4i, and then I'm going to do the conjugate of that answer. So not the conjugate of the middle sign, the conjugate of that answer. So this is going to be 3 plus 2i plus 1 plus 4i. Getting ahead of myself here. Plus 4i. So remember, we're going to do the conjugate of that answer. Looks like I'm underlining it. That's our conjugate. So 3 plus 1 is 4. 2i plus 4i is 6i. I want the conjugate of that, which equals 4 minus 6i. Notice, same answer. So you could write that. So basically what they're saying is you could do the conjugate individually first and subtract them, or you could do what we did over here, and we could subtract first and then take the conjugate. So you're going to get the same answer both ways. Okay, we're done.